as a biophysicist concerned with trying to help treat patients affected by COVID-19, I need to identify vulnerabilities in the virus to design better targeted therapies. So where are the vulnerabilities in the virus? Well, I decided to look at mutations that have pervaded and have become dominant, because I want to understand what is it that they're trying to correct. What kind of defects are those mutations trying to correct, so I can learn a little bit more about the virus vulnerabilities? Well, the COVID-19, just a matter of presenting the context here, the COVID-19 pandemic, as we all know, is posing a major threat to public health. Hence, the evolutionary change of its culprit, SARS-CoV-2, has become a matter of the utmost concern that needs to be monitored very closely. In the course of less than 6 months, mutation D614G, aspartic 614 to G, to glycine in the spike protein, has become worldwide dominant, as revealed by epidemiological evidence. So why is that? What is that telling us about the vulnerabilities of the virus that this mutation is trying to make up for? Further evidence suggests that this mutation introduces a selective advantage arising from a more stable phenotype with higher infectivity. In consonance with these findings, recent structural studies that I performed at the Daruma Institute revealed that the D614G substitution loosens up the free state of the subunits that come together to form the spike protein. So they destabilize the uncomplexed free structure while making them, the subunits, more reliant on binding partnerships to maintain the integrity of the whole protein. So the destabilization of the free subunits promotes their association, or in other words, it stabilizes the structure of the complex, right? So the subunits don't want to be free, they want to be part of the complex. So a mutation that destabilizes the free subunits makes them reliant on each other and more stable as a complex. So in this way, the quaternary structure of the spike protein, which is a trimer, is better retained after the virus activating juncture. Thus, from an evolutionary perspective, the D614G mutation probably arose to maintain the integrity of the quaternary structure of the spike protein precisely at the stage when it's most vulnerable, that is, when the main membrane fusion between the virus and the host cell takes place. So, so this may be the sort of vulnerability that we are looking at. So if the mutation is doing that, we want a therapy that reverses that, right? So we know what the mutation is trying to correct, so we know where the problem lies, and that's where we have to go to design a better therapeutic targeted therapy, right? A better therapeutic agent, targeted therapeutic agent. Within this mechanistic context, we envision that the dominant mutation hints at a new therapeutic opportunity which is maybe enshrined in a monoclonal antibody targeting the epitope involved in stabilizing the structure of the spike protein. That's another way of saying what I've just said. The net effect of this immunological treatment would be the destabilization of the virus by disrupting the quaternary structure of the spike protein when it becomes most vulnerable, that is, during the activation phase for membrane fusion, thereby reducing viral transmission efficacy. In pre-vaccination treatments to impair receptor-mediated virus uptake, currently under development, monoclonal antibodies targeting immunogenic regions of SARS-CoV-2, like the receptor binding domain, have been already identified. None of such therapies has focused on the subunit interface epitope stabilized by the G614 strain. Thus, the proposed virus destabilizing antibody falls entirely in a different category from current therapies, because it would impair viral activity following spike preactivation, so it would complement current efforts to impair virus uptake. So we are not concerned about impairing virus uptake per se. We want to attack the virus itself and destabilize it. That's a key difference in approach. And how are we going to go about destabilizing the virus? Well, we need to learn from its evolutionary history. What is this dominant mutation trying to do to stabilize the virus, so we can better destabilize it? It's like the old saying, like, if you want to defeat your enemy, you better get to know him better, right? The SARS-CoV antigen used in vaccine development aimed to induce neutralizing antibodies against the spike protein recognition of the human ACE2 receptor. Given what we currently know, it is likely that the vaccine-related antigens are closely related to the immunogenic regions used in the preparation of monoclonal antibodies. Then our own antibody, our proposal, would have the considerable advantage that it will not become redundant in the post-vaccination stage, because it doesn't target the immunogenic regions adopted as antigens for vaccination. Current therapeutic strategies are geared at inducing or directly administering neutralizing antibodies against specific immunogenic regions in the viral spike protein, in order to prevent uptake via the human ACE2 receptor. Thus, they will differ fundamentally from our proposed virion destabilizing antibody. So we have a virus destabilizing antibody which is completely orthogonal to any other effort that deals with the interface between the virus and the host cell. Because you see, our proposed virion destabilizing antibody does not target the same epitope, and none of the other therapies is geared at attacking the virion itself when and where it becomes most vulnerable. So it's a radically different approach. And I'm going to show you now a figure so you can get a glimpse of the nature of the intervention, of the therapeutic intervention at the molecular level, and how is that going to destabilize the quaternary structure of the virion and hence impair its transmissibility, which is all we care about in order to defeat this enemy. So take a look first at this slide, which shows you the exact nature of the therapeutic intervention at the molecular level using the antibody therapy. I would like to conclude by emphasizing another key difference with current therapies. So the epitope that we are proposing has evolved in the course of a few months, the time it took strain G614 to become dominant. So that that trend began in February, March, and the full dominance was achieved in late July. So it's a new epitope, quote unquote, right? And hence it is unlikely to be a terminal evolutionary product, a perfect evolutionary product. Thus, it is probably a lot easier to disrupt the new interface around the packing defect in the G614 strain than it is to disrupt the mature virus receptor complex, whose recognition interface has evolved over a far longer time period, probably in the order of thousands of years, of hundreds of thousands of years. So in current anti-COVID-19 immunotherapies, the induced or administered antibody would have to compete with evolution, which precisely at its game, right? I mean, it would have to compete with evolutionarily perfected binding partners. This is not the case with our proposed treatment. Rather than trying to disrupt the evolutionarily perfected receptor-mediated virus uptake, the proposed strategy aims at attacking directly at the virus itself when and where its structural assembly is most vulnerable. Pure and simple.